In our last video, we look at the working principle of DC motors. The major part that made up these motors were looked at. And finally, we ended off looking at what happens when a current-carrying conductor is brought to a magnetic field. In the second part of this twin series, we will be looking at how the armature converts the force experienced to torque. In the same vein, we will also be looking at effective EMF on the armature. Finally, we will be looking at how DC motors are classified based on their forms of excitation. Stay tuned. So when the current-carrying conductor is attached to a rotor, and when connected to an external circuit, the current-carrying armature conductors experience a force that is due to the magnetic field. The coil will begin to rotate as a result. Again, because the coil is connected to different polarities, the coil tends to align itself with the other poles. This is due to the induced magnetic field, which are like and unlike terms. However, when the coil is almost perpendicular to the magnetic flux, the torque action of the coil will now tend to zero. That is, the generated magnetic field will cancel each other out as a result. So the rotational torque will not be regular, which means the rotor will tend to stop when it is almost perpendicular here. So in order to have smooth running motors which does not almost tend to zero, then there is a need to incorporate additional winding. The added winding fixes the irregular rotation that occurs when the motor is almost perpendicular to the magnetic field.
Okay, perfect. It is done in such a way that, when the first coil is perpendicular to the flux, the other coil that is in the magnetic field will be connected to a DC source. And because it is connected to a DC source, the mechanical force will be experienced which will cause the coil to rotate along its axis. And the process will repeat itself in the next coil.
The second coil is used to counteract the regular rotational force that will have been experienced by the first coil when at a perpendicular position. This ensures that, at no time, balancing forces does not cancel each other out.
Now, the ring that we see here is what is called the commutator. The commutator is segmented in order to achieve unidirectional torque. Otherwise, the direction of force would have reversed every time when the direction of movement of the conductor is reversed in the magnetic field. The commutator is used to connect the armature coil to an external DC supply via the brushes. So basically, as the coil rotates, the commutator will rotate along with the coil and the brush will ensure that the rotating commutator continues to get connected to an external DC source. Now, when the armature of the motor is rotating, the conductors also cut the magnetic flux lines. As a result of this interaction, EMF will be induced in the armature conductors. The induced EMF will tend to oppose the armature current.
I was about to ask that too. Because according to Faraday's law of electromagnetic induction, whenever there is a relative movement between the magnetic field and a conductor, voltage will be induced as a result.
Of course there will be. However, in industries these days, suitable starting devices are usually used for starting and running large DC motors. The use of this special starting device is used to prevent the coil from burning out. Perfect.
The magnitude of back EMF is directly proportional to the speed of the motor. Again, in a situation when the load on a DC motor is suddenly reduced. In this case, the required torque will be small as compared to the current torque. The speed of the motor will start increasing, which is due to the excess torque. And being proportional to the speed, the magnitude of the back EMF will also increase. With increasing back EMF, the armature current will start decreasing. Again, because torque is proportional to the armature current, it will also decrease until it becomes sufficient for the load. Thus, the speed of the motor will regulate. On the other hand, if a DC motor is suddenly loaded, the load will cause a decrease in the speed. Due to a decrease in speed, back EMF will also decrease, allowing more armature current. Increased armature current will increase the torque to satisfy the load requirement. Hence, the presence of the back EMF makes a DC motor self-regulating. For small motors, which are the motors that are found in domestic equipment, the stator of this motor is usually made of permanent magnetic material. However, for large applications, an electromagnet is used. This type of DC motor is constructed in such a way that the stator is usually wound with conductors. Now, in order to fully understand why the pieces of the stator are usually wound with conductors. Naturally, metal pieces consist of electron dipoles that occur at random. Now, in order to make the metal pieces to behave as magnets, current-carrying conductor will be wound around the metal pieces. This causes the random electron to move in a common direction. So, based on the rotor constructions, DC motors are usually classified on the basis of their excitation configuration, which are separately excited and self-excited. In a separately excited motor, the field winding is fed by an external source, while in self-excited, the motor is powered from the same DC source. Overall, self-excited motors are usually divided into three, which are series wound, shunt wound, and compound wound. In the series wound, the field winding is connected in series with the armature, while in shunt wound, the field winding is connected in parallel with the armature. However, in compound motor, it is made up of a combination of series and shunt motors. That is, it consists of a series field coil which is connected in series with the armature field windings, and a shunt field coil winding which is connected in parallel with the armature field winding. Series wound motors are known to have good starting torque, but the speed will begin to drop as the load increases. Because of the series connection, the motor will have poor voltage regulation. Additional load causes more current to flow through the field coil. And of course, we know that increase in field strength results into increase in voltage. Thus more back EMF current will flow. The excess flowing current will only stop when the motor field is saturated. So basically, voltage regulation here is very poor. Shunt motor on the other has a relatively low starting torque, but it is able to run at an almost constant speed regardless of the increasing load. In shunt-connected motors, the field current is independent of the load current. Hence, an increase in armature current will not cause increase in field voltage. Here, the voltage regulation can be said to have improved. So when the load increases or decreases, it does not affect the motor torque. Because a compound, Wound is the combination of both. This will ensure that the induced voltage will be less and as a result, fair current consumption. In order to ensure good starting torque, when the motor has attained a good running speed, a centrifugal switch will switch the motor connection from series to shunt. This ensures that the motor is in good speed regulations. Brushless motor is another DC motor we have in the market today. This type of motor runs without the use of a brush. To get to know more about how this motor works, kindly check the next upcoming video. Hope you have learned something new today. See you in the next one.